Welcome to this web lecture on the transportation problem. So in this first web lecture, I'm going to introduce to you what the transportation problem is using the example of a bike sharing system on the TUE campus. And in two follow-up lectures, we're first going to look into heuristics for the transport problem, and then we're going to look into an extension which is known as the fixed charge transport problem. So first of all, let's introduce this TUE bike sharing system. So let's just assume that TUE allows us to rent bikes at one location on campus and return them at another location on campus. The problem that emerges with these systems is that they're usually eventually getting out of balance. So there might just be more people moving from the auditorium to Atlas than vice versa. So what the system operator then has to do, they have to ensure that sufficient bikes are available in all buildings. And to achieve this, they have to move bikes between buildings, and that, of course, at as little cost as possible. And this really also happens in practice. So here, for instance, on the very left, in this bike sharing system in Antwerp, you see that the bikes are just being loaded on the back of a truck, and then this truck moves the bikes between different locations within the city. So let's look at the TUE bike sharing system. So the TUE bike sharing system has stations in different buildings, and some of the buildings now have too many bikes, so a supply in bikes, while some other stations have a lack of bikes, so they have a demand for additional bikes. So what you, for instance, see that Atlas and Gemini on the left have a demand of 15 and 10 bikes respectively, while Auditorium, Luna and Vertigo have a demand of 8, 11 and 6 bikes respectively. And what you see in the middle is the transport cost. So for instance, for moving one bike from Atlas to Auditorium, it costs us 5 units. So if we want to move 2 bikes, this is going to cost us 10. So this is what you see in this instance. But now let's look into the mathematical modeling. So what we're doing for this, we're going to look into the recipe for formulations, which tells us to identify the sets, identify the parameters, introduce the decision variables, formulate constraints, and formulate the objective function. So now let's do that. What are we having in this problem? First and foremost, we have sources and sinks. That's just an artificial naming convention that we use. So usually sources is everything that has a supply, while sinks is everything that has a demand. So in our case, Atlas and Gemini are sources, while Auditorium, Luna and Vertigo are sinks. Secondly, we're identifying the parameters. So here we have a supply and a demand, which we denote as O and as D. And then we have transport costs. All of those we saw on the previous slide with denoted, for instance, by the 15 and the 10 for Atlas and Gemini. So now let's look into what a so-called parameterization is. So parameterization means we're giving values to the parameters. So for instance, we see that the O of Atlas is 15, the O of Gemini is 10. So this is just the supply that we're having at these locations that are in the set O. Secondly, our demand at Auditorium is 8, demand at Luna is 11, and the demand at Vertigo is 6. And then the transport costs, which is always given from one location to another location, is given by 5, 6, 9, 3, 7, 8. So this is something we can directly read off from this figure that we saw a few slides back. But now, let's first and foremost continue with this recipe for formulations. So once we have identified sets and parameters, we're continuing with the decision variables. And in our case, the decision variables is the number of bikes that are being transported from a source O to a sink J. So for instance, we're now transporting 1 bike or 5 bikes. The next step is identifying first the constraints and then the objective function. So let's look into what constraints we're having. First of all, we transport all bikes that are available. So in total, from any source, we're sending exactly the supply that we're having to other locations. So for instance, from Atlas, we might send 7 bikes to Auditorium and 8 bikes to Luna. This is what this constraint says. Secondly, every location has to receive a sufficient number of bikes. So for instance, Luna might receive parts of the bikes from Atlas and part of the bikes from Gemini, which is this summation that happens here. And the last part is non-negativity. So obviously we never want to ship minus 3 bikes between any pair of locations, even, and now let's come to the objective function, even if it improves our objective function, which is minimizing the total cost, given by Cij multiplied by Xij, then of course summed overall Ij that we're having, so I and O and J and D. So what I would like you to take away from this web lecture on the transport problem is, first of all, what the transport problem is. Secondly, what a parameterization is. Thirdly, we're going to look into heuristics in the next step. And lastly, we're going to look into fixed costs in the web lecture that follows after the heuristics. Thank you.